Hey everyone, this is Dr. Walker. This is video 568, Magnetic Force on a Current Carrying Conductor. In this video, we're going to look at the force on a current carrying wire. We learned in a previous video that if you have a moving charge in an external magnetic field, that it will experience a force. Well, now what we're saying is if you have a wire that carries a current in an external magnetic field, it will also experience a force. And that makes sense because a current is just a bunch of moving charges. This picture shows that when there's no current, there's no force on the wire. And then when there's a current upward, there's a force to the left. When there's a current downward, there's a force to the right. That's when the external magnetic field is pointing into the page. And we will also see in this video that this direction of the force can be predicted using the right-hand rule, just like we did when we had moving charges. The first thing that we want to do is look at the force on a current-carrying wire. The derivation comes from looking at the force on a moving charge. So let's take one moving charge here with a drift velocity v sub d and look at the force on that moving charge. The force on that moving charge is going to be Q v sub d cross b. And now we want to consider the force on a total wire, which has a whole bunch of moving charges. So we're just going to have to multiply the force on one charge by the number of charges. So let's figure out how to write down what is the number of charges. We can write the number of charges as n times v. If you remember, the little n is the number of charge carriers per unit volume. So if you multiply it by volume, then you get the number of charge carriers or the number of moving charges. And then we can rewrite the volume as the cross-sectional area times the length of that wire. So NAL. So we're almost done. Now to find the force on the wire, we can call it F sub B. It's going to be the force on one charge, Q VD cross B, multiplied by the number of charges, which is NV, or NAL. And then the last thing to remember is, I think it was in video 541 when we're talking about the macroscopic description of current, microscopic description, we had an equation for the current, which is equal to NQ VD times area. So if we look at our expression here, we have these terms, Q, VD, N, and A. So what we can do is we can rewrite this expression in a more concise form, and we're going to get the force on the current carrying wire is I L cross B, where we have defined a vector L, which has a length L, right, the length of the wire, but the direction of this vector is going to be in the direction of the current. So this is the force on a current carrying wire, a straight wire, in a uniform magnetic field. So the cool thing is that we can use the same right-hand rule that we learned about previously for the force on a moving charge to find the direction of the force on a current carrying wire. We place our fingers in the direction of the current, and before we were placing the fingers in the direction of V. So now we just place the fingers in the direction of the current. We fold in the direction of B, just like before, and then our thumb is going to point in the direction of the magnetic force. Let's look at this your turn. It says that the horizontal wire can be levitated, held up against the force of gravity if the current in the wire is going which way? So first of all, if you know that the weight is pointing down, think about the way that the magnetic force has to go in order for this wire to be levitated. Once you figure out which way the magnetic force has to go, then go ahead and figure out what direction of current will be able to make it so that there's a force in that certain direction. Go ahead and pause the video for a second, think about it. Okay, so we know that we want a magnetic force going upward to balance the weight going down. So the magnetic force is going to go upward. Now we have to use our right-hand rule to figure out what direction of current will make it so that there is an upward force on this wire. And it turns out that you should be positioning your hand just like the picture that we just saw. If your fingers are pointing to the right and you fold them into the page, since that magnetic field was going into the page, then your thumb is pointing up. So that means that the current has to go to the right in order for the force to be going upward. So that means that the current is going from left to right. The last thing that we want to look at is the force on an arbitrarily shaped wire. What if the wire is not straight? How do we find a force on that wire? So this is the expression, and I have the final product here, but basically what you do is, just like we've done when we've done electric field calculations, potential calculations, when we broke up, before we were breaking up our charge, right, into a whole bunch of infinitesimal little charge segments. Well, here we break up our current into a whole bunch of infinitesimal segments, and we call them ds. Some people call them dl. That's okay. So you just break up your wire into a whole bunch of tiny little segments, and these segments have a little length, right? The length is ds, and then the direction is going to be in the direction of the current. So we just learned before that F was equal to I L cross B. Well, if you just look at the force on one little segment, that segment can be considered to be straight since it's so small. That's the whole purpose of having a tiny little segment. So the force on that little segment, we call it dF, is going to equal to I ds, right? The length is ds cross B. And then you just integrate this over the whole length of the wire. Let's say the wire goes from A to B, and that's how you get this integral. So there's going to be a really good guided example that you really want to pay attention to. So we're going to learn how to use this equation. It's a little bit tricky, but with practice, I'm sure that you will do a great job.